Hello, everybody. My name is Mike, and I'll be the moderator for this session. Please type a question into the Q&A area so that I know you're listening. Right now, I would like to introduce Melissa Kurtz. Melissa holds an MS degree in Material Science and Engineering from Wayne State University. In her over 20 years of experience, she has served on a variety of product development teams across several industries, including transportation, medical, and consumer. Melissa has performed failure investigations on hundreds of products, which has provided her with valuable insight into common development blind spots. Melissa's topic is valuable lessons to be learned from failure. Melissa, the floor is yours.
Thank you. Thank you, Mike, for the introduction. Hello, everybody. I'm glad to be with you this afternoon and share some of my insights with you today. So a quick introduction. I know a lot of hard work goes into developing a new product, and no one intends that to fail. And I'm sure some of you recognize the image, the shoe blew out from around the world that happened with the Duke player. So no one wants that to happen. No one wants to get the reputation for having a bad product in the market. But it's a very competitive market, and in the race to innovate and get things out quickly, sometimes complexities of design are overlooked. I've seen this happen many times over the years. As Mike said, I've done hundreds of failure investigations, and so I know where and when these types of things start to occur. I've seen a theme in my investigations. I've seen the theme in people not understanding what the requirements of the product are, how the system of the product interacts with different components, as well as how the material behaves. So this is especially true with time and temperature sensitive materials like polymers, which is the focus of my material science background. So I'm gonna take a look at some of these areas, and I'll be sharing case studies with you as well for each one. You'll notice that the case studies are focused on the automotive industry, but I could easily swap out each one of these case studies with one from the medical or the consumer industry as well. So don't think it's just I'm picking the automotive industry. All right, so the first area, product requirements. So understanding the requirements for your product is critical for successful design. So if you don't know the requirements, or if the requirements are incomplete or not really representative of how a consumer is going to use it, it does run the risk of failing in the field. So your product requirements need to take in consideration how it's going to be used, intended use, but there's also potential abuse situations that be considered as far as consumer safety goes. And then also atypical use situations. So understanding maybe the odd duck and how they might use your product can provide important insights as well. Now, you might not choose to design your product for that odd duck, but it's still good to know what those are. And then you can look at the failures when they come in and say, this is one of these atypical situations. So these requirements that you have to understand, they have to know mechanical loads, cycles, electrical requirements, what the environmental conditions are. Is it going to see UV light? Is it going to see elevated temperatures or subambient temperatures, just to name a few. If these requirements aren't known, then sometimes you have to use consumer research and field testing to find out what they are. This can be especially a challenge if you're designing a new product that hasn't been in the market before, something truly innovative. In this case, then maybe even consumer research might not provide you real guidance on the requirements. One example I had in mind was the internet. If you would have gone back in time and asked consumers what they wanted from the internet, chances are they wouldn't have had a lot of answers because no one could really wrap their minds around what it is. And it definitely wouldn't be what we have today. So our first case study is going to be a fuel delivery module. So the goal of this design is to basically create a module for a new model of a small pickup truck. So this module fits in the fuel tank. This part is immersed in fuel, and there's a pump in here that pumps the fuel through the ports up here, and this is exposed on the top of the tank. And then there's also other features on it, like this float here that essentially reads the level of fuel within the tank. So historically, The flange is made from acetal. Probably doesn't mean a lot to you guys, but that's just what it was. And it has excellent chemical resistance to automotive fluids, rolled salts, and it's got good mechanical properties. I want you to keep in mind that when you're developing a new product, this kind of legacy of historical can be a hindrance, especially in innovating. The people who say, well, this is the way we've always done that, or this is the material we've always used, that can be a real trap and create a real blind spot in your design. So the product was designed, it passed validation testing, passed product testing, but then once it was on vehicles in the field, it began to see some failures. So the fuel flange that I pointed out in the previous slide, which was at the top here, this white piece with these ports, started showing cracking. It started showing cracking in the ports and adjacent to the ports. So this could result in your vehicle being stalled. It could also cause fuel to spill out of the vehicle onto the surrounding environment. So again, this design worked successfully for many years. What's going on? Why is it failing now? So part of the new model design of the pickup truck was the location of the fuel tank and therefore the fuel delivery module on the vehicle. So it was moved to location essentially that there's a gap between the truck bed and the cab. And that gap was just big enough that in certain geographic locations, certain times of day, certain times of year, that flange would begin to see ultraviolet light exposure. So that was never before a requirement for this product, but now it was. And the other thing that changed with this location was the drainage holes of the truck bed now allowed water to come out and whatever chemicals were in the bed to come out onto that fuel delivery module flange as well. So chemical resistance before was considered to be automotive fluids, road salts. It was not considered to be anything that could be carried in a truck bed. Like for example, one really aggressive chemical would be like boat hull cleaning chemicals. Those are very acidic. Or pool cleaning chemicals. Those are also very, very strong. And so now it's got to also have this resistance to these other things that weren't previously considered given this run out of the bed. So the key to successful product launch is knowing the product requirements completely before you launch. If you find out there's additional requirements after you launch, you're going to have the failures. And once you have a design, once you have a material selected and you have tools cut, changing those things is a very costly proposition, especially if you have a potential for recall, you have product in the market sitting on vehicles, because there could be liability involved in that failure. So had the designer understood these new requirements, he might have been able to select a different material, one that had contained a UV additive, or maybe even add on a shield to block the UV light and the truck bed runoff. So our second area that we're going to talk about is system influences, and this is a lot more complicated and harder to wrap your head around. It's hard to look at a product from a holistic standpoint and all the things that could interact with the other components that are there. Especially when today, a lot of times large designs are done on a system by system basis or a component by component basis with a larger assembly. And sometimes not everyone communicates and collaborates with one another. You get kind of siloed and you don't really understand what might be upstream from the part you're designing and how it might impact your part. But if we fail to try to consider the complex system influences, we're going to lead to failures unintendedly. So the first case study we're going to consider is a water valve assembly. So this is a part that's used in a heavy-duty industrial truck. It's found in the engine compartment. So the designer knows here that we need to have chemical compatibility of the plastic material of the housing for underbody chemical or unhooded chemicals, oil, gas, fuel, antifreeze, but also road salts. And he or she understands that they need to select the material according to those chemical resistance requirements. So the designer picks out a glass fiber filled acetal. I'm also not picking on acetal here, so don't get in your head that this is a bad material. But It was selected due to strength, chemical resistance, its resistance to elevated underhood temperatures, as well as manufacturability. As you can see, the housing here is in black, and then we have a copper tube that's attached to it with these 3 zinc-plated fasteners. So while the designer might have designed this component, this other in-between or intermediate components might have been something that was done by the engineer on the other side, or maybe a systems engineer working on the whole assembly. But the 3 screws here, it's important to note that those were selected to be a zinc-plated low-carbon steel. They've got good corrosion resistance. Their galvanic behavior is good in conjunction with the copper tube, and they're low cost. So the design passed the required salt spray testing, but when they put them on for vehicle testing, they started showing failures at low mileage. So what happened was, you can kind of see it on this picture here, we've got fasteners that are falling out. So this fastener fell out and allows this copper pipe basically to loosen up from the body, and it allows leakage of the fluid. And we've got some corrosion products on this one. This one you can't see very well. But the designer diligently reviewed the chemical resistance requirements. So this shouldn't have happened. So what did happen? So what the designer didn't know was that there was going to be secondary chemical exposure to zinc chloride. So zinc chloride basically forms as a corrosion product between zinc platings and road salts. And when you have zinc chloride and acetal, you have incompatibility. So this is a close-up photo of where that bolt had fallen out of the housing, and you can see you've got just glass fibers. All the resin that was there has been basically eaten away. So you're going to say to me, well, I don't understand. It passed the salt spray test. They did the corrosion testing. So it's important to understand whenever you're doing product tests, you understand their purpose and their limitations. So in this case, the salt spray test is to evaluate the time it takes for the fasteners to get to red rust. It's not intended to evaluate the chemical compatibility of the corrosion products with the housing material. And actually performing that testing, you're constantly washing away the corrosion products. So it might take 168 hours to get to red rust. You're forming zinc chloride, but you're rinsing it away so quickly because it's continuously putting water on the part. So as fast as you form it, you're washing it away again, and it's not having time to dry and to get saturated and to actually attack the polymer. This is not real world situation, because we know if we hit salt spray, it dries up and it produces a white product on the vehicle, and then it snows again later and you get more salt. So it's a cyclic test, or cyclic in the application, but not in the test. So in this case, had the designer fully understood the system influences, he could have chosen a different fastener material, such as stainless steel. Now, given stainless steel fasteners are more expensive, they're less expensive than the cost of field failures, of redesigning the housing, and as well as tarnishing the reputation of your brand. And finally, my third area to discuss is material behavior. And this is where I'm really passionate, because I see a lot of, some of these are all kind of related to material behavior as well, but you really need to understand requirements and the system influences to even start considering the material behavior underlying in all these cases. So this one is more specific to the behavior itself, and is really important, especially with a plastic material, that you really understand how time and temperature really impact its performance if you're going to have a successful product. So my case study here is a blend door that's used in an HVAC module in a vehicle. So this is in your dash, and somewhere in this giant assembly is the blend door. And that traditionally was made, in this case, was made from a glass fiber. Again, historically, was always made from a glass fiber reinforced polypropylene. So as you see in most vehicles today, the space requirements are getting more and more. So everything is trying to get miniaturized, and as things miniaturize, it generates more heat. So in this application, this new model, they were seeing higher temperatures in the case and in the blender location. So they decided to go with a more heat resistant material, which was a nylon 6,6 resin. The other change they made was they got rid of the glass fiber and opted for a glass bead filler in order to get rid of some of the warpage issues they've seen in the past with using glass fibers in this application. So FEA and product testing looked good. So they went to market with this design and they started to see field failures again at low mileage. And what they were starting to see was deformation of the blend door you see here. On the bottom of the part, you have two areas where you essentially are pivoting the door. And then this tab here is where you would actuate the door during adjustment of your temperature controls. And then around the peripheral, you'll have a foam seal that's used to seal off the door to the main chamber. And you might ask, well, what's the big deal? It's just deforming a little bit. But really, there's two things. One, the OEM specific requirements for temperature control in the cabin are very tight. And having something be deformed like this could make you run the risk of not meeting that spec. And secondly, if it deforms too much, you could run the risk of binding the blend door, and then you can't actuate it any further in the application. So the FEA and product testing looked good. So what went wrong here? So keep in mind, I said historically it had been used, they used a polypropylene resin, and now they're using a nylon. And what they didn't realize, because it was a material they hadn't worked with before, was that nylons absorb water. The water gets absorbed and it becomes like a plasticizer, and it decreases the stiffness of the material. It makes it more ductile, but it makes it less stiff as well. So when they did the FEA testing and the product testing, they essentially did it using what's considered dry as molded parts and data from the supplier. They didn't use conditioned parts or conditioned data. So one of the things we did to kind of emphasize this with them was we took a door and we did some flex testing. And you can see here at some of the temperatures that they're operating at that you're getting a significant decrease in stiffness with elevated temperature. But now once you condition that nylon door at 23 degrees C and 50% humidity, the water absorption is decreasing the stiffness of the material by about 75%. So this is a huge impact. And this difference is going to make the difference of your door deforming permanently in the field or not. So this is just really important to highlight here that when you execute your FEA simulations, you need to go beyond the data sheet. You can't just use room temperature short-term data. You got to think about how the material's behaving at the maximum continuous operating temperature of the application. How is it behaving when it's conditioned, when it absorbs water? You want to make sure that you're not just designing a product or a part that's going to survive at time zero room temperature. You want to make sure that that part and that product is going to survive out to the end of the warranty period. That might also mean taking some parts and heat aging them, or some material specimens and heat aging them, and understanding the impacts of what heat aging will have on it, or weathering, or whatever application that your part is in. The other thing is the product evaluation. So same thing, if you take a part out of a mold and you evaluate it, it could pass, but that doesn't necessarily represent what the part's going to be like a year from now. So once it's heat aged or once it's conditioned with humidity. So it's really important not to just evaluate something new and shiny, but to consider how time will impact those properties within the warranty period as well. So in conclusion, you got to go beyond just making something that looks cool and has great features. You want to make your client, you want to meet their expectations. You don't want to give something to a client or consumer that looks good and makes them feel good, but then a month later is failing. And you also want to protect the customer if there's safety issues with the product. And you also want to protect your brand's reputation. So I know I went through a lot of stuff here that's really maybe more material specific, but I think what I want to highlight is you just need to use critical thinking skills um, as you try to get the details sorted out for requirements, system influences, material behaviors. Um, we have always done it that way is a very dangerous thing, especially when you're trying to innovate and develop new products, and product requirements are always changing. So one of the things I always think of too is just because they've always done it that way doesn't also mean it's successful. You don't know that product that was designed that way 5 years ago, what the failures were or what the consumer feedback was on that product necessarily and what their complaints were. So you could be adopting design as well as, material selection that wasn't the best thing for the brand or for the product or for the consumer. So don't assume. Always seek to understand why. Always ask why this was done and why that was done, and kind of don't be afraid to probe and get answers, because sometimes people aren't thinking about it critically in the first place, and your questions might provoke them to think critically about it and think maybe we don't have to do it this way, maybe this isn't the way we should be doing it, and you can cause innovation just by asking those questions and going deeper. And then my other thing is just never stop learning. I think that don't assume, like I don't myself as well with materials. I can't assume that I know everything because materials are always changing and they're always improving, and there's always new ones out there. So I got to stay on top of it. So same thing for designers and product developers. Never stop learning more about uh, how to get to consumers and what they need, how to understand material behavior, and different ways of evaluating designs through FEA or product testing. And last slide is just questions. My email address is here if we don't get to them. And also I do invite you to follow the Madison Group on LinkedIn. We have a lot of virtual learning opportunities. Speaking of continuing to learn, we do about 3 different topics every quarter. So that's a pretty good, and covering anything from materials to FEAs to product testing. So it's a good way to learn.
Well, thank you very much, Melissa. That was a great presentation. And just to kick off the question and answer period, I'd like to refer back to your first slide, product requirements. Would you reflect for the crowd on what you know of as best practices for discovering relevant customer requirements? What's the best way to make sure you get a good customer requirements document?
I think it depends on whether you're designing a new model or a new version of a product a consumer's already familiar with. Then it might be just easy enough to do some survey type work, whether it be in field surveys or electronic. When you have a product though that's so unique that there's nothing on the market like it, you really need to get in front of the consumers, identifying kind of who your target consumer is, get in front of them and really understand what they'd be looking to have as far as features and functions out of that product. Because in those cases, you can't describe it very well. You kind of need to sit down with them and show them maybe prototypes or mock-ups that they can relate to. And it's more of a discussion, but I think it yields much richer content.
Thank you. I certainly couldn't argue with that. Here's a question. There are always new materials coming out on the market. So how can a designer be certain that they have created a testing scenario that is up to the cause?
That I'm guessing that the material supplier has created a testing scenario. Well, that's becoming harder and harder to do these days. Back in the old days when Sabic was GE, there was a lot of data that was generated around materials, and I find today that it's becoming less and less something that's generated by the material suppliers, and more something that's needed to be generated by subcontract firms, or companies that are interested in using the material. Sometimes if you get enough volume and they're willing to do that testing for you, but it becomes a matter of return on investment for them. So I think the best thing to do is if you see a material that, alternative that might work in your application, you got to really identify, okay, what is my maximum continuous operating temperature? What materials am I using now? Do I need to have creep data for this? You can kind of go through those lists, and you can, from the product requirements, you can basically funnel out and back out material requirements. That's where I always start when generating those. And then from that, you should be able to ask that supplier, can you give me this data information? Because these are my requirements. And if they can't, then I guess you have to generate it yourself, which is sometimes the case.
This is a question for me. Based on your years of rich experience, I have two questions. One would be, what is the most satisfying failure you've ever faced and solved? That's one of them. And the other one would be, yeah, let's just go with that. What is the most satisfying failure you ever addressed?
Well, there are times where you can't find a solution to the failure, and those are very frustrating, where either the failure mode is changing and it's at a 1% kind of failure rate, and it might be one or two different things that are compounding, that it's hard to separate out. But it's always good when you can actually figure out and solve the problem. I mean, the one with the fastener one there was pretty straightforward. There's a lot of that I have like that with system influences, where you get chemicals, like I said, maybe plasticizers are coming from upstream that are coming and they're cracking like a manifold in a medical application. I honestly prefer, as rewarding it can be to solve problems for people with failure analysis, I honestly find more reward in helping them avoid those in the first place. So a lot of the rewarding projects I work on are with more of the front end of development. So a new application, they need to select materials, and then how can we do that? Or we have materials selected, but we're not sure the right ones. Well, how can we test it? I prefer to work on that end because I don't want to see failures, and sometimes they can be depressing. So squirrel cage fans and automotive applications, those are depressing.
And let's see. How do you recommend communicating decisions to management that are going to lengthen the cycle of product development or raise the cost of a product? How do you have those conversations?
Yeah, that comes up a lot, because a lot of times doing the additional legwork can be more time consuming for a test, or to validate something, or it takes more time, or is more costly. And management, everyone's on a schedule as far as launch, and they don't want to move that schedule. Usually I try to present it in form of, by way of like a risk analysis, like, here's the risk we run if we don't know this, and what that could mean to the product once it does launch. And I think, most managers, as much as they are risk averse to cost and timing constraints, they're also risk averse to failure and a product failing in the field. So sometimes I try to convince them of that. If this does fail in the field, what is our option? Our option's redesign, or changing the material and changing the tools, and it take us, however many months, and take us however many dollars, and try to put it in a kind of a risk benefit cost analysis like that.
Nice. That sounds like it takes an enormous amount of diplomacy and patience.
Yes.
I'm sure data doesn't hurt either. Well, we have another minute for any more questions that might come in. We've had a number of people type in thoughts about materials and absorption failures. You've hit on on something that is near and dear to the hearts of some of the folks that we're speaking with today.
Okay,
But that
good.
wraps up our time.
All right.
Melissa, thank you so much for a wonderful, insightful presentation. I hope you've given everybody a lot of confidence to do this kind of work. Thank you.
Yes, yes. And if you have any questions, don't be afraid to reach out to me.
Have a wonderful day, everyone.